Alright, so yesterday we had looked at what are called inner product. So given vector space V, we have the notion of inner product. So vector space over F, and then with the notion of inner product. And we looked at examples where we looked at Rn and Cn. In Cn we had x and y as y star x. Here we had xy as y transpose x, the same thing, fine. From there we went to xy is equal to y star ax, all right. But at this only for A being symmetric, and with the idea that x and y are Rn itself, xy belongs to Rn. So y star is basically y transpose. Is that okay? That was the idea. But in general, you can take A equal to A star, what is called a Hermitian matrix. And then define yourself xy is equal to y star ax for xy belonging to Rn, belonging to Cn. There is no problem. What you requirement A is positive definite. This was the requirement. This is what we saw when we looked at when we looked at yesterday, we looked at some examples like we took A as A, B, B, D, and then we said that A has to be positive, D has to be positive, and determinant of A has to be positive. This corresponds to what is called positive definite, fine. So we looked at for R2, this was done for R2, you can do it for any Rn or Cn, accordingly change it, and then look at things what are called positive definite. So there is a difference between positive definite and there is a notion of what is called non-negative matrices. These are two different things, all right. This and this are two different entities. So positive definite does not mean that you are looking at entities with positive signs. What you require is, positive definite basically requires us to have that, just the definition of inner product, that x star ax should be 0 for all x belonging to Cn, all right. A is n cross n. Then I say that A is positive definite, all right, definite, if this is there for all x not equal to 0, all right, and if x is 0 then anyway it is 0 as such. So this is a requirement for you. In general, when I say something is positive, it means that I am indirectly saying that this belongs to R. This is a real number, because complex numbers you don't have 1 plus I as positive number or negative number, things like that. So in complex numbers you cannot compare objects, but in real numbers you can compare. So when you say that x star ax is positive, at the back of my mind I already have that x star ax is a real number, fine, and that is guaranteed because A is A star, but in many books you won't get the requirement that A equal to A star, because this having real number, x star ax being a real number, will imply that A has to be equal to A star, fine. But when you are looking at real numbers, then you need that A has to be symmetric. So real need A equal to A transpose, because x star ax real number does not imply that A has to be symmetric, fine. So for real numbers, A is a real number with positive definite, means that A has to be symmetric. You have to assume and then proceed, fine. So let us look at some more examples, not in this direction. In this direction I have done enough for you. We will look at some other directions. Alright, so let us do the next thing. So let us look at this. For example, I want to look at set of all 2 cross 2 matrices over real numbers, or set of 2 cross 2 matrices over complex numbers, or in general set of n cross n matrices over complex numbers. So recall that we mostly wrote it as Mn itself. Only for m cross n we wrote m cross n, otherwise we just wrote it as M2 itself. Alright. So what we can do is that I have the matrix here as say A1 1, A1 2, A2 1, A2 2. This is the matrix that I am looking at. A is this. I can have B as B1 1, B1 2, B2 1, B2 2, and I am thinking in terms of complex numbers. So I can think of AB as just multiply component wise. So A11 into B11 bar plus A12 into B12 bar plus A21 into B21 bar plus A22 B22 bar. I can do this. There is no problem, and this will define an inner product because it is thus the standard inner product for you. I would like you to see that if I look at this AB, which is equal to trace of B star A, then do I get back this? That is the question. Alright. So let us look at what is trace of B star A. So trace of B star A is nothing but, what was the trace? Trace was sum of the diagonal entries. So it is same as I going from 1 to n, B star A ith entry, which is same as I going from 1 to n. Now what is this entry? This is nothing but j equal to 1 to n, because it is an n cross n matrix, so everything will be that part. And then I have to write here B star of ij and A of, fine, ji here. This is what I will have to do, which is same as I equal to 1 to n, j equal to 1 to n. And what is B star of ij? B star of ij is, so if I look at B star of ij is same as B transpose bar of ij, which is B transpose ij whole bar, which is same as B transpose ij is same as bji. Fine. So therefore it will be nothing but j equal to 1 to n bji bar into aji. Fine. So see here ji, I is here on the right hand side and j is on the left hand side, left. Or you can interchange the two things whatever way you want, you do it. You can also write it as, because the summation is over both I and j, so I is equal to 1 to n, so you can write first j equal to 1 to n and then I is equal to 1 to n, which is aji into bji bar, or whatever way you want to write, you write it. So you can see that these two expressions are the same. Fine. So ji and bji bar, you are getting the same thing. J is 1, I is 1, A11. If j is 2, alright, and I is 1, you get this one. If j is 1, I is 2, you get this, and so on. So you can compare the two and say that they are the same thing. Fine. So somehow the trace has come to our rescue in some sense, and we can do all your calculation because at least we have understood something about trace, so some things can be said about it. Fine. So this is another inner product. Fine. Another inner product that I would like you to understand, which is very important, is, even though it's not in our syllabus, but it's used quite frequently in general. Fine. What is called, so look at all vector space V, which is C of say minus 1 to 1. So minus 1 to 1 is the domain, and C for continuous. So if you recall, I had said that set of all continuous functions is a vector space. Since it is a vector space, I can talk of inner product. It's not always possible that you can do it. Sometimes you can do, sometimes you may not do it. We look at examples where we don't have inner products. Fine. Or I can define an inner product for the finite-dimensional vector space, but then you may not be happy with it in some sense. So let's not worry about it. So what we will assume that we have inner product as far as we are concerned, and things like that. So let me look at this. So here I have got two vectors f and g which are continuous functions. So fg continuous. I can define inner product of f and g as, so f and g are functions from -1 1 to r. Fine. If it will over complex numbers, still you can do it. We will have to change it according to the definition. So this is equal to, the domain is -1 to 1, so the integration is from -1 to 1. That's one thing. And then we are going to look at gx bar fx dx. All right. So I am looking at a complex number, so the notion of bar has come. If I don't want complex number, if I want real number, that bar will go off. So I am just looking at this. So you can check here that f of gh will be equal to gf this, f of g plus h will be equal to fg plus fh. You can also check that af of g will be equal to a of fg. Fine. Now the only thing that I need to check is what happens to f comma f. So f comma f is nothing but -1 to 1 fx bar fx dx, which is same as -1 to 1 this square dx. Now this is greater than equal to 0. All right. Fine. So in integration theory, we must have learnt somewhere that when you are looking at functions which are always non-negative, that was the starting point of integration. So I am looking at -1 to 1 and the function is always non-negative. So I am looking at a function like this, and in that case I get the area under the curve. And this area, since this is non-negative, this will always be greater than equal to 0 and will be equal to 0 and equals 0 if f of x is identically 0 function. Is that okay? Now in general, when you don't have function which is continuous, if I have a function which is continuous at every point except at finite number of points, integration makes sense, but I will not be able to conclude this part that from here this will happen. That I cannot conclude because I need that. So what I am trying to say is that if I have a function like this, all right, which is 0 here, then one point is here, again it is 0 here, again another point is here, and so on. So these are the points of discontinuity. Suppose I am looking at these points, then still the integration will be 0 because look at your integration, Riemann integration, you can do that. Fine, math 101. But I cannot conclude this part. So for this to be concluded, I need that f and g has to be continuous. So therefore we wanted to continuous part. All right. The last example as far as we are concerned is that let V be a finite dimensional vector space. So it is finite dimensional. Since it is finite dimensional, I can talk of a basis of this. So let V1, V2, Vn be an ordered basis in V. Once this is an ordered basis, so any element V can be written as, so V with respect to B is some alpha 1, alpha 2, alpha n, and any u with respect to B will be equal to some beta 1 to beta n. Fine. And then I can define, so now we can define our inner product of u and v as, so v is in the second component, so it will be alpha 1 bar beta 1 plus alpha 2 bar beta 2 alpha n bar alpha n bar beta n, all right, or the usual that you do, which is inner product of, so v is on the right, so right there, so beta 1 to beta n comma alpha 1 to alpha n. Is that okay? So this is what we have. So again you can see that given an ordered basis, we are able to talk in terms of inner product, and this inner product is nothing but inner product in Rn or Cn or Fn, wherever you want to talk of, you can talk of that. Is that okay? So that's important for us, that any finite dimensional vector space can be endowed with an inner product. All right, I can always do it. Fine, and but we'll look at examples where I have something but I don't have something. That will come afterwards. So now next time what we look at is what is called Cauchy-Schwarz inequality. So many books they will write like this. Many books will use just Schwarz like this. So whatever you want to follow, you follow. I follow this Cauchy-Schwarz inequality. All right. So you follow whatever you like. I also can follow this or this depending on choice, mood. Fine, because I always forget things. So this is very important inequality. What it says is, all right, that take any vector space V and suppose V is endowed, or V has, endowed means has, inner product. All right. So whenever I have a vector space V which is endowed with an inner product, or V has an inner product, we say that V is an inner product space. So inner product space means V is endowed with an inner product. There is some inner product in V, that's all it says. Fine. So if I have such a thing, V is an inner product, then it says that look at any U and V in V, look at the absolute value of that. Fine. So let us assume that V is over R or over C. Fine. So that I can talk of absolute value here. So inner product of U and V is some scalar quantity. I am looking at the absolute value of this. It says that this is less than or equal to norm of U into norm of V. Now what is norm? I have to say what is norm of U, or this is norm of V. They are nothing but the lengths. Length of V, this is length of U. So you already know what do you mean by length as far as your dot product is concerned. So there in the dot product, the length of U of vector U was U transpose U square root, which was same as U1 square plus U2 square plus U3 square root. Fine. Now this we are changing it to U comma U. This is what we did. We just replaced the inner product U transpose U with this notation. That's all we did. Fine. So therefore when I talk of norm of U, for me norm of U will be a square root of this. Is that okay? So you can compute them. For example, yesterday we had one example in R2 where I had A as A, B, C, D. All right. No, so it was D itself. We showed that it has to be symmetry. A, B, B, D in R2, and we defined our XY inner product as Y transpose AX. Recall that I had asked you to find A such that this vector 2, 1, 2, 1, this inner product, which was nothing but 2, 1 here, A, B, B, D, 2, 1 to be equal to 1. I had asked you that find A, B, C, D, A, B, D such that this happens, and I had got your expression for this, which was I think 4A plus 4B plus D. This was one of the conditions that was required. So therefore under this inner product that I am defining here, all right, that I am defining here, this vector 2, 2, 2, 1 has length 1. All right. So we are saying that this is nothing but norm of U square, and there since norm of U square is 1 and norm of U is a positive number, norm of U is the length, so length is always a positive quantity and is 0 only when it is 0. So you can see that norm of U will also be 1. Fine. So let me write it. The norm that we are defining, norm of U is equal to a square root of UU is greater than 0 for all U belonging to wherever vector space you are looking at, equal to 0 if and only if U is 0, and this follows because of the condition that we had that u is positive for all u not 0, all right. So, that was the restriction for our inner product, and because of that we are getting that the length of u is always a positive quantity, fine. So, now we would like to prove this part, all right. Why do we need to prove it? That you can see that in our school we had learned what is called cos theta. So, we had learned what is cos theta. Cos theta was u dot v divided by length of u into length of v. So, when I am defining something to be cos theta, I will have to say that this number has to lie between -1 and u, because cos theta is a number lying between -1 and 1. So, I will have to prove that such a thing is happens, which is same thing as the Cauchy-Schwarz inequality. So, it is not true only for the dot product, it is true for any inner product. Let us try to prove that now, all right. So, let us prove it now. So, the Cauchy-Schwarz inequality. So, let v over f, so f is either r or complex number for us for the time being, be an inner product space IPS, then for all u comma v belonging to v inner product space, v length of or norm of u v is less than equal to norm of u into norm of v, right. This happens. The inequality turns to equality. So, we are saying that a star, if I look at a star, is satisfied by equality if either u or v is the zero vector, or either this is zero vector or v is equal to alpha u for some alpha belonging to f, all right. So, either they are, so in some sense we are saying that, so if you look at it, say either u or v is zero vector or v equal to lu, I can combine them together and say that u and v are linearly dependent, all right. So, recall the definition of linearly dependent. If there is a zero vector, then that set is linearly dependent, and here we are already saying that is alpha times this, and that will imply that if I take alpha to be 0, then v is 0 and things like that, fine, otherwise it is dependent. Let us try to prove it. So, proof. So, suppose, so let us look at this case. Suppose u is a zero vector, all right. Now, if u is a zero vector, this will imply that we are looking at u v inner product. Oh, I did not prove that, so I need to prove that. So, this will imply that this is 0. Now, why is so? That we need to understand that why should the inner product of u and v should be 0 when u is a zero vector, all right. So, that is an exercise, try that out yourself, fine. So, try that out, try out yourself, using the idea that 2 times u should be equal to u plus u and so on. So, try it out yourself using a scalar multiplication. All right. Or just look at this part. So, what we know 2 times u v, all right, will be equal to 2 times u v, which is same as, all right. So, what should I write? Same as u v plus u v, but u is 0. So, what we are saying is that this is same as 0 comma v, this is also 0 comma v plus 0 comma v. So, together will imply this part. One of them will cancel out and therefore, you will get 0 comma v has to be 0. Fine, that is one thing. Fine. So, if u is 0, you are done, there is no problem. So, you can see that suppose u is 0, this implies, and we also know that u is equal to 0 implies that length of u is 0, implies this is equal to this, which is same as 0 is equal to 0 times norm of v, which is norm of u into norm of v, all right. So, a star is satisfied by equality, all right. So, you can see that at least here we are able to do it, equality. Now, for the general setup, when we want to prove, I think I will just stop here. So, that is all for now. Thank you.